All right. We will, today, I want us to focus on this worksheet, which is from 5.4. Okay. So I'm going to pick out some problems for us to do off this handout. It's under today's link. It's also under yesterday's link as well. So the first page, we're just going to be solving equations, so no derivatives yet, but I'm going to circle a couple problems for us to look at. So we're going to be trying to solve for x. We're just trying to solve for x with these problems. But they kind of fall into two categories. So I want to kind of talk about them. First is that these types of problems where the variable is stuck in the exponent region, we want to algebraically move some terms around. So we want to get it so that we can get the e to the x as clean, as simplified as we can, that e to the x by itself. And then once the e to the x or e to the negative 2x is by itself, then we can involve natural log, right? Because if we involve natural log, we can have a way to bring that exponent variable down in front. And once that variable is down in front, it's a lot easier for us to solve. Okay, so that's one type that we're going to be working on. The other type is solving equations where x is not stuck in the exponent. X is stuck inside the natural log expression. So we're going to be involving e. We know that e and natural log have a way of undoing each other. So if we can involve e to get that natural log to go away, and then that allows me to get to that x a little easier. So the way we do that is we're going to raise both sides base e. Okay, but I'll go through this one at a time. But I'm going to have you guys try number 5 first. All right, so algebraically, see if you can start moving some terms around. Get it so that e to the x is by itself. So the way I want to do things today is I'm going to have you guys try some problems. I'm going to walk around, see how you guys progress, and then I'll go through the steps for each problem. Okay. If you don't have this sheet, you can just copy it down from we're just doing a few problems from each page and just kind of hitting the highlights from yesterday. Okay, so try number 5 first. Yeah. Okay, so number 5, we can subtract 9 first. Divide both sides by -2. Get that e to the x as clean as we can. And then we can take the natural log of both sides. And then once we have something in the form of natural log, that exponent can be free to move without changing anything. So once that x comes out in the front, we have a much easier time solving for x. Natural log of e is just 1. Natural log of 1 is 0. So x equals 0. Okay, try number 8. Same idea, right? Get that e to be by itself first before you involve natural log. All right, your steps look pretty good. Let me go through. So we want to get that 100 out of the way first, right? Let's clean up as much as we can before we involve natural log. So I'm going to move the 100. And now I can take the natural log of both sides. Right? And once I take natural log of both sides, now that -2x is now free to move, right? That -2x can come down in front. And then we can divide by -2. Now, something to point out, okay, you can reduce that 35 over 100 if you like. Something to point out is that this 2 cannot impact the 35 over 100, cannot impact that fraction inside natural log, right? That coefficient is in a different location than that 7 over 20. That 720 is stuck inside the natural log. It's not going to be easy to move it or change it. So you can either divide it by -2, which is completely fine. I just prefer to push my coefficient out in front, but that's just my preference. All right, so walking around, seems like you guys didn't have any issues with number 8. So now let's look at 13. Okay, so here's 13. Something I want to point out with number 13 is that we don't have an expansion property for 13. And what I mean by that is we can't do something like this. We can't distribute the natural log through and make it natural log of x minus natural log of 3. Okay, that's just not a property that's available to us. So we have to go directly into trying to solve for x. And that x is kind of stuck inside the natural log. So What if we involve e, right? What if we raise both sides base e, then we can get that natural log in e to go away, and then we can get to solving for x. So I raise both sides base e. E and natural log have a way of undoing each other. They're inverses of each other, so they're going to cancel each other out. The only thing left is the x minus 3, but we want to make sure that we balance it on the other side as well, that we raise the right side to be e squared. And then we can solve for x, right? 3 plus e squared. Okay, questions with 13. Right, look at 15 and 16, same process, but there's something that we need to do beforehand. Before we can raise both sides to base e, we need to resolve the square root for 15, and we need to resolve the square for 16. So see what you can do to maybe convert that radical to a rational, to move it, to kind of push it to the other side. We basically want 15 and 16 to be as clean as 13. We don't want any exponents. We don't want any coefficients. We want it to be as clean as this. And then you can raise both sides base e. Okay, so try that. Let me see how you do. Actually, you're almost at the end. Just solve with x. Oh, this one here. Okay. No, we can't square both sides. So this is inside, so we can rewrite this is x plus 2 is equal power. Square is something else. Right, that's a negative. Positive. That's 1/2. Okay. And then you can do that 1/2. Right. And then go 1/2. And then move the 1/2 to the other side. Once that is done, then you bend these together. And we don't want that to put this on. Okay, 15. Your work looks pretty good. Right, let's get that radical to be a form that's easier to work with. So we're going to rewrite it as to the 1/2. We could take natural log, we could raise both sides base e, but let's manage that 1/2, right? We can manage that 1/2 by bringing it down, dividing by 1/2, the same thing as multiplying by 2. Get that left side to be as clean as we can, and then raise both sides base e. That will resolve that natural log issue on the left side, and then solve for x. Okay, all right, so finish off with 16. resolve that 2, right? Bring that 2 down, move it to the other side. Once you have a nice, clean natural log expression, then you can be free to involve e to get that natural log to go away, and then solve for x. Okay, any questions there? All right, let's go to the next page. Looks like you guys are doing pretty well there. And let me highlight the problems we're going to do. We're going to do number 36, 40, 43, 45, and 46. Now 36 is, the next page is all dealing with finding derivatives. So let's start off with the easier problem, number 36. We're just trying to find a derivative for e to the negative 2x cubed. And the only thing we need to do is match the rule and to be able to apply it. So try 36. Directly into that second image. So it says the original function times the exponent. Okay, so e to the u times u prime. Okay, try number 40. Okay, now look at 40. There's something else involved besides just e to the u times u prime. What else do we have to involve here for 40? X, right? So we can't just, but it's not as easy as just finding the derivative of x and the derivative of e to the 4x. There's something else. What else is needed? Do you see a process? Yeah, product rule. We got to do product rule. So x and e to the 4x are being multiplied together. We can't merge them. So we have to use product rule. Okay, so let me spell out the things you have to find and see if you can work your way down to the derivative. Okay, check 40. And then let's try 43. F prime g plus fg prime for number 40. The rule for e to the 4x is just e to the 4x times 4, right? E to the u times u. Okay, so let me ask you about 43 though. We can't bring that 3 down without changing the value, right? This is not a natural log expression. And we prefer not to expand because that's a pretty messy having to expand 3 separate binomials. So let's think about a derivative process. What can we apply here? Chain rule, yeah. So you're going to identify your outside portion, your inside portion, and then you're going to take turns with each of their derivatives. Okay, so try that.
Excuse me, is Alex paying you today?
Yeah.
For your book photos?
Thank you. Okay, try 43. There's your outside portion, there's your inside portion. You're going to take each of their derivatives, but they're going to be in separate spaces, right? You're not going to put one inside the other. They're going to be next to each other.
show using the negative e times. Sorry, negative e to the negative t. Now, we're still inside the 3 is correct, but how do we fill out the rest of them? We put it inside the parentheses. We're going to put the original problem inside there. And then this is my next one. Okay, so what's outside the room? Well, let me ask you this. What if I ask you what is the root of x cubed? So x cubed is 3. That's the hair. Just 3 squared, 6 squared. So that's the outside portion, right? And we're about to inside after that. Plus infinity, so we do this plus that. Oh, pretty sure that's you get to the inside, you're going to be adding these together. Because that's going to be, these are separate, so you got rid of that, got rid of that, plus the so I think you can just stop here. So it's just adding these two. Yeah, that's one. And then, yeah, you basically have it, just need to change that to a plus. Oh, that's really good. No, that's good, yeah. Okay, here's 43. We have the outside derivative, which is 3 parentheses squared, right? We're just treating this like a power rule, treating parentheses as its own variable. And then in a separate space, we'll take the derivative of each of these separately. Right? So e to the negative t becomes e to the negative t times negative 1. And e to the t becomes e to the t times 1. And then there's a plus in between, so we'll have to keep that plus there. Okay, questions with 43. Okay, let's look at 45. Okay, so 45, we can't expand, right? This is not in the form. We can't distribute the natural log through. We got to jump directly into our derivative rule. We have 2 rules at play, right? You got the natural log rule. You got the exponential function base e. So which rule is going to come first? The natural log or the e to the 2x? Yeah. The larger rule gets applied first. So what you see inside the parentheses, that's your u value. So start building your u prime over u from there. also something to keep in mind is that when you find a derivative of your natural log expression, the natural log notation goes away. The only thing left is u prime over u. So unless if you want to still keep that natural log in the derivative, but that ln is not going to be there anymore.
This here, natural log.
Yeah, that's it.
No.
U prime over here.
Let's see, what's the derivative for e to the 2x? I think you're just missing that
Yeah.
portion, right? E to the 2x. Okay. Check 45. Look at 46. So 46 looks like it's a similar setup as 45. It's just that it looks like our u value is a little messier than 45. But maybe there's a way to avoid this messy u value. Notice that this is part of the natural log expression. So is there anything that we can maybe do beforehand to make our derivative maybe easier down the road? Expand. Yep. You got some expansion properties, so let's take advantage of it. Okay. We have natural log of a over b can be expanded into natural log of a minus natural log of b. We can separate that fraction into individual natural log terms. Now we got to do derivative twice, but then they're both going to be easier than having to deal with this original setup. Try 46. And when you expand, we haven't done the derivative yet, right? It's still going to be y equals. But then once we get past that expansion, then we can look at our derivative rules. Okay. U prime over u. And then e to the x, we can apply that derivative rule as well. Okay. U prime over u for both my terms. Okay. Any questions here? Okay, next page, number 50. Now 50 is not part of a natural log expression. We can't expand it. Maybe we can go directly into a derivative rule. So what do you think we can apply just from the very beginning?
Yeah, you got the numerator and denominator, so we can jump directly into quotient rule, right? Okay, f prime g minus fg prime all over g squared. Now, once you find the derivative, let's not worry about cleaning up. You can just leave your derivative unsimplified. Any questions? All right, does anybody still need to look at 50? Good. Okay. Got one more problem for us. So this is a little bit longer, but I will kind of help us along the way as we get there. All right, so here's our problem. There's number 66, a few pages down. Okay, let's talk about this problem here. This is one is where we want to find the tangent line equation. So the big picture is that from this equation, we're going to find the derivative. From the derivative, we're going to use the order pair to find the slope. Once we have the slope and the order pair, we can put it in point slope form and try and get down to a linear equation. But the challenge here is getting to the derivative portion, right? So look at how this is set up. What are some things that we have to involve as we move towards our derivative process? Look at how this is set up. What do you see? Or let me ask you this. Is there anything that we can do before we find the derivative? Anything that could make this easier?
You can expand the natural log of x log.
Good. We can expand, right? That will make things easier. We can split that natural log xy into two separate terms. We're going to have an easier time with derivative. Good. One more thing that stands out. There's a process that we have to involve here. Right. Look at the variables involved. What do you see? Yeah, two variables. And then you see a couple of y's involved, right? So we have to involve what? Implicit, right? So implicit means that we're going to have some dy dx's that pop up along the way. And we have to kind of rearrange and solve for dy dx. Good. How many y's do you guys see? 2. That means when you find the derivative, you're going to have 2 dy dx's when you find the derivative. Okay, so let's start here, expand, and then move into your derivative step, and see if you're able to make progress. And I will show each step after you guys try it, so you can kind of update your progress.
Yeah, that's good, that's good. Right, okay, so why don't you try it? What do you think e to the x minus y will turn into? Original problem, no changes, right?
Yeah.
Times u prime, so what do you think the derivative of x minus y will be?
dy dx 1 minus 1.
Okay, close. Let's do this separately, right? What's derivative of x?
1.
Okay, what's derivative of y?
1.
But we also need to involve what?
dy dx.
There we go. So it's 1 minus dy dx. And that's going to go in its own separate region to the right of it. Yeah, this is a lot more involved here, right? Because you got the chain rule within an implicit and a lot more things going on. Okay, so here's my expansion step. And then my next step is my derivative, right? I know that the natural log of y will produce its own derivative or its own dy dx. We know this is going to produce its own dy dx. Okay. So this is what we have. We'll take each term and apply the appropriate derivative for each term. So the 1 is a constant, so it goes away. I just left that out. It just disappears. Natural log of x, right? We can apply our rule, u prime over u, so just 1 over x. Natural log of y, we can also apply this rule, right? So 1 over y, but because we just took y's derivative, we need to make sure we include the dy dx. And then e to the x minus y, we're just going to kind of use this rule to kind of help us chart our progress. So e to the x minus y, your derivative involving y will always be the original problem. So you're always going to copy down the original problem. The original term is always going to be part of your derivative. And then we look at the exponent. So the exponent, we got to take its own derivative separately. So x becomes 1 and y becomes dy dx. So that completes the calculus portion. The rest of it is trying to move things around to get dy dx by itself. But things are not easy to move the way that it stands because the dy dx that we want to kind of move is stuck inside this bracket. So we got to distribute that term e to the x minus y through first. Once we distribute through, then we're going to have 4 independent terms, and then we can start moving the independent terms around. Dy dx on the left, everything else on the right. So once I distribute the x e to the x minus y through, now you can see I have 4 individual terms, and I can pick out the dy dx terms that I need to that we want to have next to each other. So I'll add the e to the x minus y over to the left side, group the dy dx terms on the left, move the non-dy dx terms on the right. Then we can factor out the dy dx, and then work our way down to our derivative. But even when we reach the derivative, we're still not at the end yet. We still have to work our way to our tangent line equation. But I'll just pause for a moment and see if you guys have any questions. Okay, so once we're sitting at the derivative level, how can we use this to help us get to our slope value? How can we work our way down to a numeric slope? Is there something that we can use to plug in?
You can plug in the point.
Yeah, plug in the point, right? It looks messy, but it'll work its way down to a number. So take your ordered pair, 1, 1. One in for X, one in for Y, and see how far that cleans up. Okay, keep in mind, anything raised to the 0 power is not 0. Anything raised to the 0 power is going to be 1. Things will clean up all the way down to a slope of 0. Our equation is going to be simpler than other equations because the slope is 0. And then do point slope form. All right, any questions? So tomorrow, we're going to explore derivative rules that are not base E. So we're going to look at derivative rules that are base 2, base 3, base 5. They all can be subcategorized as bases other than E. And the nice thing, the derivative rules will look a little messier than these rules, but the nice thing is that we can think of these as kind of parent derivative rules, because whatever we're dealing with other bases, it just kind of be built on top of this rule. So we'll look at some more derivative rules tomorrow. And then Friday, we can do some curve sketching, kind of going back to the parts that we skipped over. And then Monday through Wednesday, test review, and Thursday, next Thursday is our Chapter 5 test. All right. If you're on Teams, you're free to go. Have a great day. See you tomorrow.